All right, so today I'm going to give you a little bit more history about molecular visualization, but really this is leading up to a discussion about molecular visualization software that I'll start introducing to you after break. I'm going to show you a couple of different molecular visualization applications that I use on a regular basis and that I think are really helpful to the medical illustrator. But I'm gonna start out by just giving you a little bit of historical background about our understanding of the three-dimensional structure of molecules, because you're going to encounter a lot of information about the different imaging technologies that are used for imaging molecules, and I find that it's very helpful to have some understanding of those imaging technologies, especially X-ray crystallography, X-ray diffraction, because you'll see a lot of information related to that when you're looking at molecular models. In particular, there's a database online called the Protein Data Bank where you can go and retrieve three-dimensional models of protein structures. And the vast majority of the structures that are in that database were solved using X-ray diffraction. And there's information that you can see and read about the molecules, as you're looking at the Protein Data Bank. And as I say, sometimes it's helpful to understand that and understand a little bit about the technology that was used to create those 3D models. So if you go back to the early part of the 20th century, prior to the teens, the 19 teens, we knew very little about the three-dimensional arrangement of atoms and molecules. We had some sense of the 3D structure of some molecules. There was a chemist named Emil Fischer who came up with something called a Fischer projection, which explained some of the optical properties of molecules. Like if you shine polarized light through a crystal, it bends the polarized light in a distinctive pattern, and you can explain the bending of polarized light as it goes through a crystal based on some of the geometry of the crystal structure, of the molecular structure. But besides that, we really didn't know much about the 3D arrangement of atoms in a molecule. And for the 100th time, I'm going to mention to you that atoms are smaller than the wavelength of visible light. So we can't see atoms. We can't see how those atoms are arranged into a molecule. So we need some other technology to allow us to peer inside of a molecule and actually see the three-dimensional arrangement of atoms in a molecule. And a big breakthrough occurred in the 19 teens. In 1911, a physicist named Max von Laue recognized that X-rays have a much smaller wavelength than visible light, down to around like 10 to the minus 10 meters. Remember that visible light has a wavelength in the range of 10 to the minus 7 meters. X-rays are down around 10 to the minus 10 meters, which is about the size of a hydrogen atom, which means that anything bigger than a hydrogen atom, you can, quote unquote, see with X-rays. And he proposed that because X-rays have this smaller wavelength, that you might be able to use X-rays to actually determine the three-dimensional structure of molecules. And literally within months after Max von Laue published that observation and this theory that you could use X-rays to study the crystal structure or study the structure, the 3D structure of molecules, someone actually used that technology or used that theory, put it into practice, and was actually able to determine the 3D structure of a molecule. So 1912, it was actually less than a year after von Laue, William Lawrence Bragg, who was working at Cambridge University. There's a physics lab at Cambridge University known as the Cavendish Lab, which I'll mention again later because it's been a hotbed of this kind of 3D structural biology research, molecular biology research. So he actually created a practical mechanism to use the diffraction of an X-ray beam, the fact that an X-ray beam is bent as it passes through a crystal, to then determine the crystal structure of sodium chloride, or common table salt. And what he determined was that a crystal of table salt looks like the picture you see on the left, where you have alternating rows of sodium ions and chlorine ions. X-ray diffraction is an amazing tool, and we'll talk about it for a while today, and then talk about how it's allowed us to solve the structure, the 3D structure of even some very complicated molecules. But one downside to X-ray diffraction is that in order for it to work, you have to be able to get the molecule to crystallize. And a crystal is just a repeating pattern of, well, somebody want to turn your volume down on your computer if that's what I'm hearing. I don't know if that's maybe the overhead. It's just the overhead volume that's giving that echo. So you have to be able to get a molecule to form crystals. And as I was starting to say, a crystal is just a repeating pattern of individual atoms, or for a larger molecule, you actually have to get the entire molecule to repeat itself in a regular geometric pattern. So again, what you're looking at on the left is a crystal of table salt, sodium chloride. And you see that the crystalline structure of that is the crystalline structure of sodium chloride is literally just these repeating rows of sodium and chlorine atoms, but repeating in a very, very regular geometric pattern. On the right, you have some crystals viewed under a microscope of another common product that most of you probably have in your house or your apartment. It's common table sugar, or sucrose. Now, sucrose is a much more complex molecule than just sodium chloride. In sodium chloride, you've just got two atoms, sodium and chlorine, that just alternate to create the crystal structure. When you create crystals of sucrose or table sugar, it's literally the entire sucrose molecule that is repeating itself in a regular pattern. Sucrose is what's known as a disaccharide. It's actually composed of two smaller sugar molecules stuck together. Sucrose consists of a molecule of glucose and a molecule of fructose stuck together. And glucose has, I don't know, 20 atoms or so. Fructose has maybe 20 atoms. So you're talking about a molecule that's maybe got 40 atoms, and then that entire thing has to repeat itself in a regular pattern to make these sugar crystals. Some other examples of crystal structures would include things like diamond and graphite. Now, the interesting thing about diamond and graphite is that they have the exact same chemical structure, or the exact same chemical composition, I should say. Diamond and graphite are both 100% carbon. They are just pure carbon. So if you try to do some kind of chemical analysis, if you could somehow dissolve a diamond or dissolve graphite or something like that and break it down into its components, all you get is just a bunch of carbon atoms. What's different between diamond and graphite is the crystalline structure. And if you look down at the lower left, what you see is that in a diamond, you have this pattern of the carbon tetrahedra, where every carbon is bonded to 4 other carbons in 3-dimensional space. And those covalent bonds between the atoms are very, very strong, which is why diamond is the hardest naturally occurring substance, the hardest substance known to man. Graphite, on the other hand, is also just repeating carbon atoms, but each carbon is bonded only to 3 other carbons, and they're arranged in these flat sheets. And the flat sheets are very slippery. The sheets can actually slide relative to one another, which makes graphite very, very soft. There's a scale that's used in geology called the Mohs hardness scale that is a measure of the hardness of a substance. So the diamond is a 10, which is the hardest thing. Graphite is like a 2. It's an extremely soft mineral. And in fact, graphite, because those planes can slide easily relative to one another, graphite's actually used as a lubricant in some industrial applications. You can coat, surfaces with graphite to make them extra slippery. So, very, very different properties of these two crystals just based on the crystal structure. So X-ray diffraction would allow you to generate an image to show this three-dimensional arrangement of the carbon atoms in either diamond or graphite. So let me talk to you a little bit about the technology of X-ray diffraction. I'll be the first to admit that I don't completely understand the process. I have a basic understanding of how it works, but there are some aspects of it. There's some very complex mathematical analysis that's involved in X-ray diffraction, which I certainly don't expect you all to know. There's something called a Fourier transform that's involved in actually interpreting the data from these X-ray crystallography studies or X-ray diffraction studies. That's the part of it that I don't claim to understand, but I do understand the basics of how the process works and a little bit about the theory behind them. So what you're seeing at the top of this picture is a crystal of some substance. Anything that you can get to crystallize, you can stick in the middle of one of these X-ray diffraction machines. And surrounding that crystal, the gray circular thing surrounding the red crystal, that is a metal capsule that is lined with a sheet of photographic film. And you take a source of X-rays, you need something that's actually going to generate a beam of X-rays. You shine that beam of X-ray into the device, the X-ray is going to pass through the crystal, and the X-ray beam is going to be diffracted, meaning it's going to be bent by the repeating layers of atoms or repeating layers of molecules within the crystal. If you look at the bottom of this image, take a look at the bottom left, what you're seeing there, the squiggly lines represent the X-ray beam traveling into the crystal, and the little rows of green circles represent some kind of repeating element within the crystal. It could just be rows of identical atoms or rows of entire molecules that are repeating themselves inside this crystal. Those rows of repeating objects inside the crystal act as what's called a diffraction grating, which is something that is actually going to bend the X-ray beam. Oh, and by the way, I forgot to mention, the reason I drew the X-ray beam as a squiggly line is to show the fact that X-rays are one of these forms of electromagnetic radiation that travels in a wave form. So the squiggly line is representing the wave form of the X-ray beam. And remember, with electromagnetic radiation, the thing that distinguishes one type of electromagnetic radiation from another, like one color of light from another color of light, or infrared from ultraviolet, or gamma rays, or whatever, the thing that distinguishes the different forms of electromagnetic radiation is the wavelength. So the distance between the peaks of those little squiggles in the orange line, that's the wavelength of the X-ray. And you can see from this illustration that the wavelength is, I probably should redraw this sometime. The wavelength is actually bigger than those atoms, which doesn't make sense. The wavelength should actually be smaller than the atoms. But now in that bottom left picture, I've actually shown two different beams of X-ray radiation entering the molecule, coming down from the left and entering those layers of green repeating dots. And if you look very closely at the squiggly orange lines at the far left, where the beam of X-ray is coming down into the rows of green dots, the waves are what we call in phase. Actually, maybe I should, sorry for the folks on Zoom who can't see me, but I'm going to come up to the front of the room and point this out. The peaks of one wave, the peak of the wave lines up perfectly to the peak of the wave right next to it. And the trough, the bottom of the wave on this beam, lines up perfectly to the bottom of the wave right adjacent to it. And that's going to be true as this X-ray beam shines into the crystal. Every little waveform, they're all going to be in phase. Meaning all the peaks are going to line up with all the other peaks, and all the troughs will line up with all the other troughs. But then as the X-ray beam is bent, as it's diffracted, as it passes through the these rows of repeating atoms or repeating molecules, the beams of X-rays are diffracted or bent at slightly different angles. And as they exit the molecule, as they exit the crystal, notice now that the peak of one wave lines up with the trough of the wave next to it, and the trough of one wave lines up with the peak of the wave next to it. And you'll just have to take my word for this. I mean, the physicists could prove it to you. Those things completely cancel out. So even though there is energy coming out in the form of X-rays, those X-rays would have no strength. They wouldn't do it. You can prove this with sound waves too. Like sound is also a form of energy that travels in waves. And if you produce the same frequency of sound and you have two different speakers that are out of phase from one another, like all you have to do is just move one speaker a little closer to the listener than the other, the sound waves will literally cancel one another out and you won't hear it. Even though both speakers are making noise, if the waves are perfectly out of phase, they'll completely cancel the sound energy and listeners will hear nothing. Same thing happens with X-rays. So as this X-ray beam strikes these rows of dots, many of the diffracted waves of X-rays are actually going to be canceled out. On the other hand, depending on the exact angle at which the X-ray beam hits the rows of dots, there are going to be other angles where the X-ray beam that is being diffracted or bent as it comes out of the crystal, they're now going to be in phase as they come out of the crystal. And all it depends on is just the angle at which the X-ray strikes this layer of repeating molecules. So as the X-ray beam is diffracted out of the crystal in this second situation here on the right, the peaks of one wave line up with the peaks of the wave next to it. The troughs of one wave line up with the troughs of the wave next to it. This has an additive effect. The energy of those adjacent waves is actually going to be multiplied, increase. And that X-ray is then going to strike the piece of photographic film on the inside of the X-ray diffraction chamber. And photographic film responds to X-rays the same way that it responds to light, visible light. It's going to expose the X-ray film. And you then develop the X-ray film the same way that you would develop an ordinary piece of photographic film. And what you see on the X-ray film is a bunch of black dots, which just represent the precise angles at which the diffracted beam is in phase and has enough strength then to actually expose photographic film. Yeah.
If it exposed the same way as the program film, then why you cannot have its ways
Right, because X-rays, the only way you can do that is you have to sort of artificially assign a color to the X-rays. You have to say, okay, this wavelength of X-ray we're going to call green. This wavelength of X-ray we're going to call blue. Right? X-rays themselves, because they're not visible, have no color. Same thing with electron microscopy. We talked about that, the fact that electron micrographs are always racing. Because all you're seeing in an electron micrograph is where there are electrons and where there aren't. There's no such thing as color because the electrons have very different wavelengths than light.
It's not like full color of the organs. Oh no, there
In orbits, right? There's a color lookup table where you assign a color to a particular shade of gray. So it is an imaginary thing where we say, okay, we're just going to say that this shade of gray, we're going to call that blue, and this shade of gray, we're going to call that red. But there is no color in it. Yeah. So, so you can use this principle to actually determine the spacing between the rows of repeating objects in the crystal. And there is a mathematical formula, and I know as soon as I went and mentioned the word math, sometimes eyes roll back in their head and they stop paying any attention, but it's actually, you know, if you know a little bit of algebra and a teeny bit of trigonometry, it's a really simple formula. This is actually called the Bragg equation, named after the divine Bragg. And it's B equals 1/2 lambda over sine of theta. So what are the variables? Well, B is literally the distance between the repeating objects in your crystal. What's actually forming this diffraction grating, causing the X-ray beams to bend or diffract at the fastest light. So you can determine B, you can determine that spacing between repeating objects in the crystal if you know lambda. Lambda is the wavelength of the X-rays that you're shining into the crystal. And you know that because the person running the experiment can actually control the wavelength using whatever device they're using to generate the X-ray beam. So you actually have control over the wavelength that you generate. So you know lambda. Theta is the angle. And remember I said that you only produce diffracted waves that are in phase. You're only going to get one of these black dots at certain very specific angles between the crystal and the beam. So you can determine the angle theta by simply looking at the position of the black dot on the photographic film. The black dot is going to be rotated a certain angle away from horizontal, right? And that's the angle over here on the right is equal to the angle over here on the left. I'll use both the angle theta. So just simply measuring the position of that black dot on the photographic film, you can figure out what the angle theta is. So we know the wavelength of the X-rays, we know the angle theta to measure it directly off the photographic film, plug it into that simple equation, and you get D, which is the distance between repeating objects in the crystal. And for something like sodium chloride, where all you're talking about is repeating rows of sodium atoms and chloride atoms, this is relatively simple. Of course, I say that now. You know, for somebody like Max von Laue and William Lawrence Bragg, who figured this out back in the 19 teens, it was pretty dramatic discovery. So this is actually what the, whoops, if the projector will catch up to me. That's really annoying. That's never happened to me before, that we have such a lag time. There we go. This is what an X-ray diffraction apparatus looks like. The one on the left is the actual device that William Lawrence Bragg used in 1912 to solve the structure of sodium chloride. I love these old machines. I mean, they're so primitive looking. It's hard to imagine that that was a state-of-the-art, sophisticated scientific instrument at the time. Looks like something your grandpa would build in the basement. But it had everything it needed. It had a source of X-rays, it had a place to put a crystal, and it had a place to put a piece of photographic film to detect the diffraction of the beam, the X-ray beam. On the right is a more contemporary one, which actually looks like a piece of sophisticated scientific apparatus. But there's that round circular thing in the middle is the chamber that would be lined with a piece of photographic film. And then they obviously did some kind of motion here. I don't know if it's some sort of stop motion photo or something like that, but there's actually this one actually doesn't use photographic film. This uses a sensor, kind of like a digital camera, to detect the X-rays. But this is what the pattern actually looks like on the piece of photographic film. It's basically just this circular piece of film with a bunch of black dots on it. And each of those different black dots corresponds to a different value of D, a different distance within the molecule. Maybe I can do this back here instead of pointing at the board. So this thing that looks like the letter Q here, that's because apparently this computer doesn't have the font that I used when I did this at home, when I created this PowerPoint at home. That's supposed to be theta. So that's supposed to be that angle theta. And as I was saying before, you can simply measure up from the center of the piece of film to determine that angle theta. And same thing down here. It's sine of, gosh, it doesn't have any of the Greek letters. The Bragg equation is D equals 1/2 lambda. That's supposed to be a lambda, and then it's supposed to be sine of theta. But you just measure from the center of the piece of photographic film, you just measure up to one of these black dots, and that gives you your angle theta. And like I said, we already know what lambda is. That's the wavelength of the X-rays. So you just plug that into this simple equation, and you come up with a value for D. But every one of these black dots represents a different value of D. And if you look at something even very simple, like the sodium chloride table salt crystal, so you've got some rows of sodium atoms, shown here in red. You got some rows of chlorine atoms, shown in green. So you have spacing between a row of sodiums and a row of chlorines. That's one distance D, which would be represented by one of the black spots on here. You have another distance that I've called D2, which would be the distance between a row of sodiums and the next row of sodiums. So D1 was between sodium and chlorine. D2 is from sodium to the next sodium. That's actually going to create a different diffraction of the X-ray beam and produce a different dot on the X-ray diffraction pattern. D3 is the spacing between repeating rows of chlorine atoms. That's going to create yet another D. Now you have spacing between atoms in a vertical direction, but you also have spacing between atoms in a horizontal direction. And so if you rotate the crystal to a different angle, now you're going to get repeating distances between the sodium atoms in a different orientation, and between chlorine atoms in a different orientation. And even when the crystal is rotated on a diagonal, you're going to get a row of alternating sodium and chlorine atoms, and another row of alternating sodium and chlorine atoms. There's going to be a different value of D for this kind of diagonal rows of repeating atoms. So this is not actually the diffraction pattern for sodium chloride. I couldn't find a copy of William Lawrence Bragg's original X-ray diffraction pattern. I don't know what this molecule is for, but it illustrates the point that when you do X-ray diffraction on a molecule, even something very simple like sodium chlorine with just two elements repeating, you actually get multiple distances, multiple values for D. The tricky part, which is the mathematical part that I don't claim to fully understand, is I understand how you get to this point. I understand how you get a bunch of values of D. But how do you then mathematically work backwards from all these different values of D to figure out the actual geometric spacing of the atoms within that crystal? Maybe I could wrap my head around it for something simple like sodium chloride, but you get into a more complicated molecule, and then it becomes even more challenging to figure out, okay, how do we determine the actual 3D structure of the molecule from just knowing a whole bunch of D values, a whole bunch of spacing values? Well, I put this slide in here to show you an important concept. This is one of the things that you'll probably run into as you're using databases like the Protein Data Bank. This is a piece of information that you're going to see repeatedly in that database, and it's one of the reasons that I'm giving you this whole explanation of X-ray diffraction. So on the previous slide, we saw what an X-ray diffraction pattern looks like. It's this circular piece of photographic film with these little black dots representing places where the X-ray beam was in phase and actually exposed the photographic film. Here's another representation of that. This is kind of a simplified schematic of that. And what we're looking at here on the left side of this image is just one quadrant or one quarter. So imagine that we took just one quarter of this X-ray diffraction pattern. You might notice that it's symmetrical. It's symmetrical from top to bottom, and it's also symmetrical from left to right. So really, you only have to analyze the dots in one quadrant, one quarter of this complete circle to figure out your structure. So here we're looking at just the bottom right quadrant of one of these X-ray patterns. And what you see are all of these dots corresponding to different angles of theta, different angles at which the X-ray beam was diffracted. And then each of those then corresponds to a different distance d within the spacing of the atoms within the molecule. When scientists started putting more complicated molecules into one of these X-ray diffraction devices, what they found was that the number of reflections, or really diffractions, of the X-ray beam started to increase dramatically. Even a molecule which is not particularly complicated, like this is a molecule on the right, it's a benzene ring with two NH2 groups, two amino groups, and then there's a chlorine atom, which is the big atom. That's not a especially complicated molecule, but even something with that many atoms, which isn't very many, it's 6, 7, 8, 9, 10, it's maybe under 20 atoms, will produce a rather complex X-ray diffraction pattern like the thing you see over here on the left, with lots of dots. Because you have to realize, going back to this other image here, even something very simple, you have many different spacings, many different values of D. So as your molecule gets even just a little bit more complicated, the number of values of D starts to go up dramatically, and you get lots more spots in your X-ray diffraction pattern as the molecule gets a little bit more complicated. You get up to something like a protein, which a protein may literally have thousands of atoms, and you can actually get proteins to crystallize. So you've got repetition of a molecule that has thousands of atoms in it. You get literally tens of thousands of diffractions of the X-ray beam. Even a relatively simple protein would produce an X-ray diffraction pattern with more than 25,000 individual dots in it. Well, trying to do that Fourier transform, trying to do that math on, say, 25,000 dots, it just becomes enormously complex. You could probably do it today using a supercomputer, but back in the early days, even when computers came into existence in the 1940s and 1950s, it was way more than what those computers could calculate. So one way that crystallographers simplified the process of converting these dots into a molecular structure is they started out by just looking at the smaller values, the smaller values for the angle theta. So the black dot in the upper left here, that represents the center of our X-ray pattern. So that represents that little white hole in the middle of the X-ray pattern. So that's the black dot here in the upper left. The X-ray dots that are close to that center correspond to small values of the angle theta, right? So the Again, if we look at our X-ray picture here, if you have a small value of the angle theta, that means you've got a dot that's very close to the center. And then as you get dots that are farther away from the center, those correspond to larger values of the angle theta. Well, if you put a very small value for theta into that Bragg equation, you get a larger value of d. So what that means is the dots that are closest to the center of the X-ray diffraction pattern represent large values of d, atoms that are spaced farther apart in the repeating pattern of your crystal. So the scientists who were doing these early X-ray diffraction studies, they would make their lives a little bit easier by doing the math and solving the structures only for these small values of angle theta, in other words, the dots closest to the center, and that would give them large values of d, large spacing between atoms. Well, it's kind of like the concept of resolution in Photoshop. If you have something with very, very low resolution, you're going to get a very fuzzy image that's not very detailed. As you increase the resolution in Photoshop, you can get something that has a lot more detail to it and a lot crisper edges. So same thing with X-ray diffraction. As you solve small values of theta, you're getting large values of d, you're getting a crude, low resolution picture of what the molecule looks like. So these things that you see over on the right-hand side of this image, these are what are known as electron density maps. And so using this map that I don't claim to fully understand, you can take a pattern of dots like you see on the left and actually create a map that shows where there are dense clusters of electrons, because it's actually the electrons orbiting the atoms and orbiting the nuclei, that's actually what's responsible for the diffraction. So if you solve the dots that are closest to the center, you notice here in the picture on the left that there's a value of 2.20 here. So what that means is that the dots closest to the center within that circle that says 2.20 correspond to distances or values of 2.2 angstroms or more. So that's giving you a picture of this molecule at a resolution of about 2.2 angstroms or larger, which is actually like kind of low res crude image. You can then refine the image more by starting to analyze more dots that are farther away from the center. So this next circle represents values of d, so small values of theta, or excuse me, progressively larger values of theta that correspond to progressively smaller values of d. So if you analyze all the dots that fall within that circle that says 1.54, you get a map of your molecule at a resolution of 1.54 angstroms, which is, finer resolution. Same thing, you go out, analyze more dots, you'll go all the way up here to 1.19. You get an even more detailed map with finer resolution, where we can now see the structure of the molecule at a resolution of 1.19 angstroms. And then finally, when you analyze all of the dots in this case, we get a really, really detailed map of where the atoms and electrons are located at a resolution of 0.77 angstroms. So as I was saying before, the reason I'm bringing all of this up is when you go into a database like the Protein Data Bank, you're going to see this resolution value listed with any molecule that was solved by X-ray diffraction. You're going to see this d value, and maybe I could have simplified this and not bored you with so much physics and math, but smaller is better. Smaller d values mean a finer resolution, more accurate image. if you find a model, if you find two different models of the same molecule, and one of them has a resolution of, say, 4 angstroms, and the other one has a resolution of 1.8 angstroms, go with the 1.8. Because that just means it's a finer resolution model. All right, so that is a rough overview of the technology of X-ray diffraction. It was used extensively throughout the 20th century to solve the three-dimensional structures of lots and lots of molecules. I mean, it started in 1912 with William Lawrence Bragg, but at that time you could only solve the structure of relatively simple crystals. And then over the course of the 20th century, especially with the advent of computers that could crunch all that math, you were now able to solve the structures of progressively more complex molecules. And one of the most famous stories in the history of science that relates directly to X-ray crystallography was the race for DNA in the 1940s and early 1950s. So at that time, there were a number of laboratories around the world that were trying to solve the three-dimensional structure of DNA. We didn't know that it was a double helix yet. We knew what DNA was. We knew that it consisted of nucleotide bases. We knew it consisted of adenine and thymine and guanine and cytosine. In fact, in the early 1950s, there was an article published by somebody named Erwin Schargraf, who was the first to demonstrate that the amount of adenine is always equal to the amount of thymine, the amount of guanine is always equal to the amount of cytosine. That was actually a very important thing to know when trying to solve the structure of DNA. But it wasn't until the early 50s that we figured out, oh yeah, adenine binds to thymine and guanine binds to cytosine. That's why they're present in equal numbers. So in the late 40s and early 50s, one of the people who was working on this was my old buddy Linus Pauling, who I talked about a lot in the previous lecture. So after he had won his Nobel Prize for solving the quantum mechanics structure of the chemical bond and determining the van der Waals radius of the elements, he gave up on quantum mechanics and decided to move into protein chemistry and started, organic chemistry. He was looking at proteins and he was looking at DNA. And he did X-ray crystallographic studies on DNA. And unfortunately, he hadn't quite figured out the trick yet to getting a good X-ray picture of DNA. In fact, most people hadn't figured out the trick yet, and I'll tell you the trick in a minute. They were all getting what turned out to be inaccurate X-ray pictures of DNA. And so based on this bad X-ray diffraction data that Linus Pauling was getting at Caltech, he thought that DNA was a triple helix, 3 strands of nucleotides coiling around one another to form a triple helix. And he thought that the sugar phosphate backbone was in the middle and the bases all faced out towards the outside of the triple helix, which really was probably one of his few really big mistakes, because there's no way chemically that could possibly happen. But the X-ray data was telling him that that's what the structure was. At the same time that Pauling was working on this at Caltech, 2 people that you've probably heard of, James Watson and Francis Crick, they were working in the Cavendish Physics Laboratory at Cambridge University, the same laboratory where William Lawrence Bragg had originally developed X-ray diffraction. They were working in that same laboratory trying to solve the 3-dimensional structure of DNA. And they also hadn't figured out the trick. And they also came up with a model very similar to Pauling's model of a triple helix. The person who knew the trick was Rosalind Franklin, who was working at King's College in London with her colleague Maurice Wilkins, shown in the picture also. And what Rosalind Franklin had figured out is that the DNA needs to be hydrated in order to give an accurate picture of its 3-dimensional structure. What that meant was you needed water present around the DNA to help the DNA maintain the proper structure. Now, I have no idea how she figured that out. But she was conducting her X-ray diffraction studies under very high humidity to maintain some hydration, maintain water in the DNA structure. And she was able to get what eventually turned out to be much more accurate pictures of the structure of DNA. And I think she knew before Watson and Crick that it was actually a double helix with the bases facing in. She was a very cautious, very careful scientist. She would not publish anything until she was really sure of herself. So even though she was producing really good X-ray data, and she had probably figured out that it was a double helix at this point, she was taking her time, being very careful and very meticulous. And she didn't like Watson and Crick. I mean, they weren't at the same university, but they were both in England, so they knew one another. She thought they were brash and cocky. They were the kinds of guys who would publish research without being careful and cautious. And so she intentionally kept her data secret from them and didn't want to share her data with them because she was afraid they would simply take her data and run with it and publish it and kind of, go off half-cocked and publish it and not necessarily, get it right. But as the story goes, unbeknownst to her, her colleague Maurice Wilkins, also at King's College, shared her X-ray data with Watson and Crick, even though she didn't want to. And they saw it and they immediately recognized it was a double helix and immediately went to work on building their model. I'll show you a picture of the model that they made in just a minute. And figured out that the bases, the sugar phosphate backbones on the outside, the bases face inward. They were aware of Erwin Schargraf's research showing that adenine always equals thymine and guanine always equals cytosine. So when they built their model, they had adenine facing in and forming hydrogen bonds with thymine, and same thing with guanine and cytosine. So they were then able to determine the three-dimensional structure of DNA. And rushed it to publication. It was published in April of 1953 in the journal Nature, which was the most prestigious scientific journal at the time, probably still is. Published it in Nature. When Rosalind Franklin found out that they had gotten hold of her data, she realized that they were going to get it to publication before she did, and they'd ultimately get credit for it. So she scrambled to write up the results of her own research, submitted that to Nature right after Watson and Crick had submitted theirs. Maurice Wilkins wrote his own article, submitted it to Nature. So if you ever want to hit the lottery, find someone who's getting rid of volume 171 of the journal Nature, because that will have their 3 articles in a row in the April issue of volume 171. I keep looking for it, but it sells for about $15,000 on online these days, so I'm not going to spend that much money. But the articles were printed in the same issue of Nature in the order in which they were received. So Watson and Crick's article was received first, so it appears first, followed by Franklin's and then Wilkins, or maybe Franklin and Wilkins are the other way around, I forget, but Watson and Crick's appears first. So they were given, what's called priority in science. They were the ones who were primarily credited with the discovery, even though they were really using Rosalind Franklin's data. Another little twist to the story. So Rosalind Franklin went to a scientific conference in 1951 or 52, I forget the exact year, but sometime, shortly before this stuff was published in Nature. And Linus Pauling was supposed to attend the conference. And there's some conjecture that she most likely would have shared her X-ray data with Pauling, who probably would have immediately recognized it was a double helix and recognized that his triple helix model was wrong. And it's very possible, of course, this is just conjecture, speculation, but knowing that he would have figured it out immediately if he'd seen her data, there's a very good chance that he might have been the first one to publish it, in which case he would have won his second Nobel Prize. He did eventually win another one, which I'll tell you about later. But you know, he would have actually ended up with 3, because he would have won a Nobel Prize for DNA also. The reason he didn't go to that conference is because it's actually related to his to his other Nobel Prize. After the dropping of the atomic bombs on Hiroshima and Nagasaki at the end of World War II, he recognized the destructive power of atomic energy. Of course, I mean, he's the guy who kind of solved the bonding structure of atoms, so I guess if anybody would know, he would. And he ended up writing a little book called No More War. It was an anti-war book, all about the dangers of nuclear war. And this is at a time when Joe McCarthy was chasing so-called communists around the US and blacklisting them. And if you write a book called No More War, clearly you must be a commie. So they took away his passport and prevented him from leaving the country because they had suspicions that you know, surely he must be working with a communist if he's writing a book, an anti-war book. So he was prevented from traveling to this conference. And like I said, had he gone, yeah, maybe he would have solved the structure of DNA before anybody else. We don't really know for sure. So believe it or not, this is what all the controversy is about. This is Rosalind Franklin's photograph 51 that she took in 1951 using X-ray diffraction. That's the double helix structure of DNA. You couldn't prove it by me, but you know, apparently the folks who worked regularly with X-ray crystallography, they could look at that and somehow know right away that that's a double helix. So this is the data that was leaked from Franklin's lab, leaked by Maurice Wilkins to Watson and Crick. So here they are again, standing with their model. I think I showed you this photo way back on the very first day of class, because I was talking about how important constructing a model, whether it's just a drawing, or in this case, a 3-dimensional physical model, how important that is to the process of discovery. So they created little objects out of metal and cardboard to represent the nucleotide bases, you know, the adenine, the thymine, the guanine, the cytosine, and they created the sugar phosphate backbone of the DNA molecule out of, you know, just little sticks and things, creating kind of like a little stick model, and constructed this large apparatus, this large model of their, you know, their idea of what the DNA model looked like. And I always forget who's who. I always forget which one's Watson and which one's Crick. But if you look behind them on the wall, there's a little drawing, and I don't know how well it shows up there, up on the projector, but it's a drawing, kind of like a ribbon drawing of the double helix. It shows 2 spirals coiling around one another with all the bases in the interior. Which, if you could see it better, you'd realize it looks a lot like, you know, modern pictures of DNA. That was actually drawn by Francis Crick's wife, Odell, who went by the nickname Odie. So Odie Crick created that ribbon diagram of DNA, which then appeared in their article in Nature in 1953. This is the entire article that revolutionized the field of biology. Just 1 page in Nature. The molecular structure of nucleic acids, a structure for deoxyribose nucleic acid, by James D. Watson and Francis H.C. Crick. And there's that picture of the DNA double helix drawn by O.D. Crick. And they do actually give credit in here to Maurice Wilkins and Rosalind Franklin for their experimental results. But there's a great line from this article which I just love. I think it's one of the best quotes from the history of science. It's kind of understated, but it was eventually going to revolutionize the entire field of biology. It has not escaped our notice that the specific pairing we have postulated, in other words, the pairing of adenine to thymine and guanine to cytosine, immediately suggests a possible copying mechanism for the genetic material. So they recognized even then, as soon as they built this model, that one strand of the DNA double helix could act as a template for the production of another strand of DNA by simply matching up the adenines to the thymines and the guanines to the cytosines. And the other strand simultaneously could also act as a template for then replicating the DNA. So they recognized that immediately when they saw that picture. 9 years later, after these 3 articles were published in the journal Nature, James Watson, Francis Crick, and Maurice Wilkins received the Nobel Prize in Physiology and Medicine for solving the 3D structure of DNA. Notice that Rosalind Franklin is not included in that. Now, people have often claimed, oh, this is like the ultimate example of sexism in science, that, poor Rosalind Franklin was left out, even though it was her data. But there's actually a weirder reason why her name was not included. She died before the Nobel Prize was awarded. She died of cervical cancer, which was probably related to working around X-rays. And the Nobel Prize Committee does not award prizes posthumously. So you may have created the greatest thing since sliced bread, but if you die before they get around to giving you the Nobel Prize, they don't give you one. So they don't award Nobel Prizes to people who passed away. So since she passed away a few years before the prize, she wasn't recognized in that. So I got a couple of chats here. Let me just see. Okay. Thanks, Sheila. Fun story for International Women's Days. F those guys. I'm not sure Sheila wanted me to share that, but yeah. Oh, another chat. She's probably saying, Jim, I can't believe you shared that. Okay to share. Okay. All right. So that's the story of the use of X-ray diffraction to determine the 3-dimensional structure of DNA and how important and revolutionary that was. X-ray crystallography was also, come on, get this thing to work here, important in determining protein structure, but it took a few more years to solve the 3D structure of a protein, because it turns out that proteins are way more complicated even than DNA, way more complicated than nucleic acids. One of the biggest challenges with doing X-ray crystallography on proteins is just getting a protein to crystallize. In order to get a crystal of anything, you have to purify it. You have to have basically water and then a solution of pure whatever it is you're trying to crystallize. So if you're trying to make crystals of sodium chloride or table salt, you need nothing but water and sodium and chlorine. And then when you dehydrate the water, the salt forms crystals. Same thing with sucrose, sugar, table sugar. You need sugar and water and nothing else. And when you evaporate water, you get sugar crystals. Well, same thing with protein. You need to purify the proteins and then gradually let them grow crystals. And number one, trying to purify proteins is tricky. I mean, there are newer technologies that make that a whole lot, I won't say easy, but they make it easier than it used to be. back in the early part of the 20th century, it was a challenge just to get some proteins to crystallize. But then the other thing is that the protein itself is enormously complicated. I mean, as I said before, some proteins have thousands of atoms in them. I mean, some proteins have thousands of amino acids, and each amino acid itself has, a dozen atoms or 20 plus atoms in it. So you're talking about, in some cases, maybe tens of thousands of atoms. So the number of unique reflections that you get in the X-ray crystallographic pattern, the X-ray diffraction pattern, is just enormous. It's in the tens of thousands of reflections. So it takes, powerful computers a long time to solve all the math to start to give you a picture of what the protein structure looks like. Interestingly, one protein that actually crystallizes very easily is myoglobin, which is present in muscle cells. And people were crystallizing myoglobin even in the 1800s. I don't think they really knew what it was necessarily, but you can take earthworms and squish them up in a petri dish, and the liquid that's left behind will spontaneously start to form crystals of myoglobin that come out of their muscle tissue. So myoglobin is one that does crystallize very readily, and there are a few other proteins that do crystallize readily. Hemoglobin is another one that also crystallizes readily. And we'll see in a few minutes that those are some of the first proteins to be solved using crystallography. So William Lawrence Bragg, as I mentioned earlier, had figured out the basics of X-ray crystallography in 1912 and had solved the structure of a really simple molecule like sodium chloride in 1912. Over the next couple decades, chemists all over the world just started taking anything they could find and sticking it into one of these X-ray crystallography devices to try to solve the 3D structure of it. And there was a scientist named William Asbury. He was actually a scientist working at the University of Leeds in the United Kingdom in England. And turns out, I guess Leeds is in an area of England where they raise a lot of sheep. And they're raising the sheep specifically for wool production. And they make a lot of wool garments in this part of England. And so the University of Leeds actually has a whole institute for the study of textiles. And William Asbury was a scientist in that textile institute. And what he wanted to do was take any kind of fiber that is used in the production of textiles and clothing and start trying to subject it to X-ray analysis, X-ray diffraction. So he took things like silk, and he took wool, which of course wool is just hair. Hair is made out of protein called keratin. Silk is also a protein. So he took all of these different kinds of fibers, many of which are made out of protein, and he subjected them to X-ray crystallography. And he found that no matter what kind of protein fiber he put into his X-ray crystallography device, whether it was wool or silk or human hair or any of a number of other things, he would always get one of two distinct patterns. One pattern he called the alpha pattern, and it had a couple of different reflections of or diffractions of the X-ray beam that corresponded to spacing of approximately 5 angstroms, and then another dot corresponding to a spacing of about 9.5 or 10 angstroms. Then some other fibers he would put into this X-ray crystallography device, and he would get a different pattern that he called the beta pattern. And this had spacings of like 3.3, 6.6. Well, 6.64 is just a multiple of 3.32, so that's probably just the same thing repeating itself. But then he got a couple of other spacings as well. And one other interesting discovery he made is you could take a fiber that had the alpha pattern, and if you heated it up and pulled on it and stretched the fiber out and then did X-ray crystallography to it, it now adopted the beta pattern. So some fibrous proteins already had just the beta pattern. I think silk, for example, had the beta pattern without having to do anything to it. But things like keratin, from human hair and from sheep's wool, they had the alpha pattern initially, but as soon as you heated them and stretched them, the alpha pattern changed to a beta pattern. So he reasoned that the beta pattern represented just a linear chain of amino acids in a straight line, and the alpha pattern somehow represented a folding of the amino acid chain into repeating units, which you see there at the top. And when you heated up something with that alpha pattern and pulled on it, you were stretching that protein chain out into its primary structure, into just a straight linear chain of amino acids. But that was as far as he could get with it. He didn't have any further understanding of what these structures looked like. All he knew is you could stretch out a protein from the alpha pattern into the beta pattern. It wasn't until 20 years later that my buddy, Linus Pauling, figured it out. He realized that the so-called alpha pattern was in fact the linear sequence of amino acids, but those linear chains of amino acids were lying side by side, forming beta sheets, which is something we talked about last time. And I'll show you the picture of it again, just to remind you what a beta sheet is. But it's where the amino acid chain continues straight for some distance, then does a sharp hairpin turn, 180-degree turn, goes back the other way, then does another 180-degree turn, goes back the other way. Well, let me jump ahead and show it to you. The beta sheet is on the right. So you've got the linear sequence of amino acids running one direction, then it does 180-degree turn, goes back the other way, turns around again, goes back the other way. And these adjacent chains are then organized into a big flat sheet. And the beta pattern that William Asbury was seeing back in the 1930s was simply the spacing of the individual amino acids in the primary structure of the protein. The other thing that Pauling recognized at the same time in the early 1950s was that the beta pattern that William Asbury was getting was a helical spiral of amino acids called the alpha helix, which I introduced you to last time also. The alpha helix and the beta sheet are two components of what we call the secondary structure of the protein. It's where the straight amino acid chain begins to fold itself up. And the alpha helix, each complete twist of the spiral has a spacing of 5.1 angstroms, which is the alpha pattern that William Asbury was seeing 20 years earlier. So Pauling was recognized for discovering these. He published, I can't remember if it was one article where he described both of these structures or two separate articles in 1951, where he described these two aspects of protein secondary structure. But it still took a little while longer, it took a few more years before you could then solve the structure of an entire protein. And that was finally achieved in the late 1950s, by two people. The first protein structure was solved by this guy, John Kendrew. We'll talk about more in a minute. And then the second protein structure was solved by his colleague, Max Perutz. John Kendrew and Max Perutz were also working at the Cavendish Physics Laboratory at the University of Cambridge. Same place where Watson and Crick worked, same place where William Lawrence Bragg had used X-ray diffraction to solve the structure of sodium chloride back in the teens. Kendrew and Perutz were both, I think they were both like postdoctoral researchers working in this lab. And their research advisor wanted them to work on the structure, the 3D structure of proteins to see if they could figure out, the 3D structure of an entire protein. And the research advisor, I think, recommended that they use two different proteins that crystallize very easily. I already mentioned these earlier. Myoglobin, which is a molecule that stores oxygen in your muscle tissue. That's the one, like I said, if you just squish up a bunch of earthworms, the myoglobin crystals will just begin to crystallize spontaneously. Well, what they discovered is that you can get a lot of myoglobin from sperm whales. I guess whaling was still legal back in the 1950s. So I guess in England, you could go down to whatever the big whaling city was, and you could get yourself some sperm whale meat. And sperm whales have huge concentrations of myoglobin in their muscle tissue, which is what allows them to dive deep down in the ocean and stay submerged for over an hour without breathing. Whales are mammals, they gotta come to the surface and breathe, but a sperm whale can dive for over an hour. It might be 2 hours. They can stay submerged without breathing because they have so much myoglobin in their muscle tissue, they can store a huge amount of oxygen in their muscle tissue. So you got myoglobin, you get a big chunk of sperm whale meat, you squish it up, and you get lots of nice myoglobin crystals. The other protein that these two guys were going to work on was hemoglobin. And turns out you could get a lot of hemoglobin from the local glue factory, which is where they would send horses and cows when they get into their older years to be slaughtered and all their body parts ground up and turned into either glue or gelatin. But they had to do something with the blood. So they went to a glue factory and they collected a whole bunch of horse blood from this slaughterhouse. And you could then, I guess, you had to probably do something to it because you had to break open the red blood cells to get the hemoglobin out. Because the hemoglobin, of course, is packaged in the erythrocytes in the red blood cells. But you could then get crystals to form from horse hemoglobin. So you've got sperm whale myoglobin and you've got horse hemoglobin. Somebody had to pick one, so I believe the story is that they literally flipped a coin. And Kendrew got the better end of that coin flip because he got assigned to study the structure of myoglobin, and his buddy Max Perutz got assigned to study hemoglobin, not knowing that the hemoglobin molecule consists of 4 almost identical protein chains, each of which is very similar to myoglobin. So Perutz was solving the structure of something that was basically 4 times the size and complexity of myoglobin, but they didn't know that at the time. So what you're looking at here on the left is John Kendrew's first low-resolution crude model of what the myoglobin protein looked like. You remember earlier in today's lecture, I was talking about the fact that you could solve fewer of the dots in the X-ray pattern. You could do the math on a smaller number of dots to start getting a kind of a low-resolution crude picture of what the molecule looks like. And then over time, you do more math, more computation, and gradually get progressively finer resolution, more detailed pictures. So that twisted blob of white tubes that you see there is a low resolution model of myoglobin at about 6 angstroms resolution, which is very low resolution. Turns out every one of those white tubes that you see is an alpha helix. It's a coiling spiral of the amino acid chain. And on the right side, you see a drawing that actually shows, it's not quite in the same orientation, but pretty close. Actually, I think it's rotated 90 degrees now that I look at it. But that's a drawing by an artist named Irving Geis of the low resolution model of myoglobin. But the artist then drew in the spiraling of the alpha helices, the spiraling of the amino acid chain within each of those white blobs. The red circle thing, that represents the heme molecule, which is the part of myoglobin that actually holds the oxygen, the O2 molecule in muscle tissue. It turns out that hemoglobin has that same heme structure, although each hemoglobin molecule has 4 of them. So, like I said, this was the low resolution version of the myoglobin molecule. Kendrew then continued to do more math, analyze more dots in the X-ray pattern, and eventually was able to build a high resolution model that literally had every single atom in the molecule in its correct geometric location. And the way he would do that is he created this, he referred to it as a forest of steel rods, little metal rods sticking up out of a piece of wood. And he had those maps that I showed earlier, the things that look like topographic maps, they were called electron density maps. He had generated those from the X-ray data, and he would place those X-ray, or excuse me, those electron density maps in amongst all these steel rods. And the electron density map would then show him, okay, there's an atom located here, and he would put a little clip on one of these metal rods right at the location of where one of those atoms would be. And then he went about the process of actually building a little ball and stick model in amongst this little forest of steel rods. And then when it was all done, he just removed all of the metal rods, leaving this behind. That's a photograph of the actual model that he built, consisting of just these little sticks representing the individual atoms. It's really kind of hard to orient yourself and tell what you're looking at. You just see a whole cluster of little sticks. The white string, though, that is winding its way through the molecule is essentially a backbone model. The white string is showing the folding of the amino acid chain within this compact blob of a protein. And that red ball that you see kind of in the middle of the molecule, that is the iron atom that's in the center of the heme group, which is what actually holds the oxygen. On the right is a painting of that same model, almost in the same orientation, pretty close. And this was a painting by Irving Geis, the same guy who did this illustration on the right. Irving Geis was an interesting character. He was originally trained as an architect and ended up doing a lot more work as an illustrator. And he did a lot of work for Scientific American in the late 1950s and the 1960s. And he was assigned to do a lot of these paintings of these early 3D structures of molecules. And I believe the painting on the right appeared on the cover of Scientific American in about 1960, shortly after Irving Geis published, or excuse me, shortly after John Kendrew published the structure of his myoglobin protein. All right, why don't you all take a break, because I've been talking for an hour and 25 minutes. So take about 10 minutes. And then we'll resume. All right, I'm gonna get back in here and share. Okay. So, oh, it keeps doing that. Okay. All right. So I left off talking about John Kendrew solving the three-dimensional structure of sperm whale myoglobin. So this is the first protein where we actually could see the complete three-dimensional structure, the arrangement of all of the atoms within the molecule. This was published in 1958. And I was telling you the story about how John Kendrew and his colleague Max Perutz had maybe flipped a coin to decide who got which molecule. It took Perutz a couple years longer to solve the 3D structure of horse hemoglobin because it's basically 4 myoglobin molecules stuck together. So it's basically 4 times as complicated as myoglobin. It's 4 roughly identical chains, protein chains being held together in a tertiary structure. The picture on the left is another one of these low resolution models. It's different from the white blobs that Kendrew had, but the principle is the same, that it's a lower resolution model. And then on the right, I don't have a picture of the actual high res model, the actual stick or ball and stick model, but I do have this painting that Irving Geis did. Remember I mentioned he was the one who painted that stick picture of Kendrew's model. So this is a painting of it, and if you look closely, you can see the atoms, the individual atoms in there, and each of those red or pink tubes is an alpha helix, and so there's a spiraling coil of amino acid chain within each of those little pink tubes, and then that in turn is folded up to make a tertiary structure, and then you put 4 of these similar chains together to create the overall quaternary structure for a functioning molecule of hemoglobin. So that was published in 1960. So by 1960, scientists had solved the structure of only 2 proteins, just myoglobin and hemoglobin. 3 years later, I don't recall exactly which research groups solved these other structures. I don't know if it was still the folks at Cambridge University in England, or if there were other groups that were now starting to do this, but 3 years later, only 3 more protein structures had been solved. By 1968, only 3 more had been solved. So basically by the end of the 60s, we only had maybe 10 proteins that have been solved in 3 dimensions, 10 protein structures. And it's a testament to just how difficult this was. I mean, doing the X-ray crystallography was hard. Having so many reflections, so many of those little dots on the X-ray pattern that have to be analyzed to start to get any kind of reasonable model of the molecule just required tremendous computer processing power. And back then, you know, a computer would take up an entire room. Like this whole room would be a computer, which now is probably you know, not even as powerful as what you have on your wrist. You know, if any of you have one of those little iWatches or anything like that. But it took a lot of computing power, and then the actual creating the model, you know, whether you know, had that forest of steel rods and you had to put little clips to represent the location of every individual atom, just that process of creating the model was very intensive. Nevertheless, even though the progress on solving protein structures was very, very slow throughout the 60s and early 70s, it was recognized that eventually it would be nice to have a place to keep all of this data, have some kind of repository for the structural information about these molecular structures. And so in 1971, the Protein Data Bank was created. It was originally created at Brookhaven National Laboratories, which is part of the US Department of Energy, located down on Long Island. That was the original location of it. It was really just a bunch of computers that stored data about molecular structures. When it first opened, there were only 2 protein structures deposited in the Protein Data Bank, and just a handful of new protein structures were gradually added to the Protein Data Bank each year for the next several years. Now, eventually, the pace of change started to accelerate, and now there are hundreds of thousands of protein structures stored in the Protein Data Bank. And it's one of the main databases that we'll use in this class to find molecular models. So shortly after the structure of complex molecules was solved, things like the structure of DNA and the first protein structures. There were other scientists who were working on ways of representing these protein structures digitally. And some of the earliest work on this was done by a guy named Cyrus Leventhal at MIT. And these are some photographs of the setup that he had. There was a big mainframe computer that probably took up the size of this room. And there was a little terminal, which you can actually see in the middle of the left photo. Looks like a giant typewriter. You would type data into the computer through this terminal. And then what you had to do, though, is you still had to build a physical model the same way that John Kendrew or Max Perutz did. You still had to build that model with all the little sticks in it. And then you literally had to measure the bond angles and the bond lengths and everything for the position of every atom in that model. So you actually had to go to the trouble of creating a physical model, then measure it, and then enter that data back into the computer to create this representation. You can actually see one of these space filling models sitting on the desk over here, and you see a screen, which was really an early oscilloscope, an early progenitor of today's computer monitors. And you see there's actually a little stick representation. It's a backbone model of a protein being displayed on that early computer monitor. This little thing that looks like R2-D2 here in the foreground, this little dome here, that was actually an early attempt at creating a trackball. If you're familiar with a trackball, it's like a big ball that it replaces a mouse. You know, you roll the ball around and it moves your cursor around on screen. Well, the way this thing would work is you'd put your two hands on that glass dome and gradually tilt the dome one way or the other, and it would cause the molecule to rotate in three-dimensional space on that early computer monitor. Well, jumping ahead a couple of decades, into the 70s and into the 80s, there were more sophisticated computers that were developed and software that was designed specifically for molecular modeling and molecular visualization that would run on some of these more sophisticated computers. Still primitive by modern standards, but much more advanced than the computers in the 1960s. One in particular was manufactured by a company called Evans and Sutherland. Didn't take up a whole room, but it was still a great big monster of a computer. You can see the primitive keyboard that this guy's working on, and then the primitive computer monitor. But there was a piece of software that was written specifically to run on an Evans and Sutherland system. There's a piece of software called Frodo. And what Frodo did was it took the X-ray crystallography data, those values of the angle alpha, theta that you would measure directly from the X-ray crystallography image. And it would do all of the math for you and actually generate a digital version of the three-dimensional structure of your molecule that you were interested in. So it was no longer necessary at this point to build a physical model, measure it, and then enter those measurements into the computer to create a digital model. You could now take the X-ray crystallography data directly using this program called Frodo, and then create your digital model of a protein or some other complex molecule. Apparently, the estate of J.R.R. Tolkien didn't appreciate them using the name Frodo, so they forced them to change the name of the software. They renamed it just O. I read an article several years ago that said that it's estimated that about 95% of the protein structures in the protein data bank, and as I said, there are now hundreds of thousands of them, about 95% of those protein structures were determined using Frodo or O. And it's still around and it's still widely used for determining 3D molecular structure from crystallographic data, from X-ray diffraction data. Jump ahead another decade, get into the early 90s, and personal computers were now becoming very popular. There had been some really primitive personal computers released back in the 70s. Things like the MITS Altair, the Amiga and Atari system, the Commodore, the first Apple computer, the Apple II, was first released in 1977. This is before the Macintosh. This was just an Apple computer before the Mac itself was released. You had the IBM PC, and lots of other early computers. But by the early 90s, your two dominant computer platforms at that point, at least for personal computers, for desktop computers, you had the Mac, and then you had the IBM PC and all of the IBM PC clones running DOS, MS-DOS, which was before Windows came into existence. So there were some early attempts to create molecular visualization programs that would now run on these desktop computers. And one of the first ones that was released was a program called MAGE, which was designed exclusively for the Mac, or initially designed for the Mac, and was released in 1992. It was produced by David and Jane Richardson at Duke University. You might remember Jane Richardson's name. She was the person who popularized the ribbon model of protein structure. And I showed you some examples of her ink drawings of ribbon models in my previous lecture. Dave and Jane Richardson were also the publishers of a new journal that was released around the same time. There was a journal called Structure, which was, I believe, the first journal devoted specifically to structural biology. In other words, understanding the 3D structure of biological molecules. And they copied this little program, this MAGE program, onto a little floppy disk and actually distributed it with the very first issue of their new journal, released in 1992. So they basically gave away this software for free to anybody who wanted it. And so it started to spread and catch on very quickly among biochemists, molecular biologists, and so on, or what they called structural biologists. A year later, a guy named Roger Sale over in England released a program called RASMOL. Now, he had originally written it to run on a Unix mainframe computer, but then created a version that would run on the Mac, released that in 1993, and it was called RASMOL, or RASMac was actually the Mac version of it. And you see a little screenshot of RASMOL. These are actually screenshots that I took on my own computer, because I used to run RASMOL on my computer. And so that's just a screenshot that I took of it. It was primitive, it was simple, but it was surprisingly powerful. And this is right around the time that I first started to get into this kind of molecular visualization stuff, was 93, 94, 95, in that era. One of my personal favorite programs to this day, I mean, it doesn't work anymore because you can't find a computer old enough to run it anymore, but I love this piece of software. It's called WebLab Viewer Lite. It was actually based on RASMOL. So in 93, this guy, Roger Sale, released RASMOL, and he released not only the application for free, but he released the source code, meaning anybody could copy it and then use it to build new programs, new software. So this program called WebLab Viewer Lite was actually based on RASMOL, but with some refinements. Another screenshot from one of my old computers. You see, it's also pretty simple. I mean, there's literally 5 tools in the toolbar, and just a tiny handful of menus, but it allowed you to visualize a molecule as either a stick or ball and stick or a space filling model. You could even put a surface, like a solvent accessible surface on the outside of the molecule. So you could visualize it using all these different kinds of models. There were options to change colors. You could change the color of elements. You could use some of the other color schemes that I shared with you last time. And one of the coolest things about WebLab Viewer Lite was the fact that it let you export the model as a VRML file, which stands for Virtual Reality Markup Language. And it's a 3D file format. And by exporting a VRML file out of WebLab Viewer Lite, you could then take that VRML file and open it in 3D software. And, I don't think Maya existed back then. I know Cinema 4D didn't exist, but there were other 3D programs. There was something called Stratavision 3D, and a couple of other programs. And, so I was dabbling in 3D back then, mostly for molecular rendering and molecular visualization. It was released by a private company called MDL Information Systems. A year later, that same company, MDL Information Systems, they released another version of WebLab Viewer Lite that was called Chime or Kime. I've never been able to figure out whether it's pronounced Chime or Kime. Probably we'll call it Chime, but it's short for chemical mime, which is why sometimes I want to pronounce it Kime, because it's that hard C sound. But anyway, this was it was a plugin that you could install into your web browser. I mean, in 1996, there was this newfangled thing called the interwebs, and you could install this MDL Chime plugin inside your web browser in Microsoft Internet Explorer or Netscape Navigator. You guys have no idea what I'm talking about. These were old web browsers. And it allowed you to actually view 3D molecular models right inside of a web page. And so this is actually viewing a molecule of ATP in a web page, and you could right click and bring up this menu to rotate the model around, change how you displayed it, ball and stick or space filling or whatever, and you could save the molecule. You could save it as a VRML file directly out of Chime. So jumping ahead to the modern day, skipping a couple of decades, there are lots and lots of molecular visualization tools out there that are available to you, and they do lots of different kinds of things. Most of what we're going to work with in this class for the remainder of the semester are things that fall under this first category of molecular visualization tools that simply let you view an existing molecular model. Many of these allow you to view molecular models right in a web page, so similar to that Chime program that I just mentioned. But these are more contemporary web-based viewers that utilize things like JavaScript or OpenGL, which are, OpenGL is like the rendering language, I think that's built into a lot of computers these days. I won't bother you with the names, you can read them there. But if you go to something like the Protein Data Bank, you can view those protein models in one of these different web-based viewers. And then those web-based viewers, some of them will then let you export the model and download it to your computer. There are also standalone programs that you would run on a desktop computer. Every time that I open up a molecular model and show it to you, I'm using a program called Chimera, which is one of my personal favorites. That's one that I'll be demonstrating to you in this class and teaching you about. There's another one called VMD, which is short for Visual Molecular Dynamics. That's one that I used to teach in this class, but we've been having trouble getting it to run for some reason. So we're going to skip it. It was my least favorite anyway, so it's not a big deal if we skip over VMD. PyMol is another one. PyMol is really popular with chemists. I'm not as big a fan of PyMol. I much prefer Chimera myself, but a lot of people in the chemistry business seem to prefer PyMol. And then there are molecular visualization tools that plug into a 3D modeling program. They actually act as plugins inside a 3D program. So unfortunately, another one of these is one that I was hoping to show you that we can't get to work. It's called EPMV, or Embedded Python Molecular Viewer. the reason it doesn't work anymore, the reason we can't get it to work in here is that the people who create EPMV, they haven't released an upgrade to it in a long time. And so it's no longer compatible with the newer versions of Cinema 4D or Blender, any of the other programs. There's another one though called Molecular Maya, which is a plugin that runs inside of Maya. Now I'm not a big Maya guy, so I've never really used this myself. So I won't be introducing it in here, but it's good to be aware of it in case you want to try playing with it yourself. So those are all things for viewing molecular models. There's another group of programs that are called chemical drawing programs, where you can actually draw your own molecule. It'll allow you to draw rings and bonds and put elements in. You can draw your own molecule in 2 dimensions, and then the program will automatically calculate the bond angles to create a 3-dimensional representation of that molecule, and then let you export it in various 3D formats that you could then bring into your favorite 3D modeling software. We're going to actually play with one in here called Marvin Sketch, but there's some others, ChemDraw, Spartan, and others that do the same thing. I like Marvin Sketch because it's free. And then finally, there are things called computational chemistry programs that we definitely won't be dealing with in here. I'll just mention them very quickly. They're called computational chemistry programs because they will compute or calculate various properties of a molecule just based on its 3D structure. So they can calculate things like, electrical polarity, like what's called a dipole moment in a molecule. They can determine what parts of the molecule are hydrophobic, which ones don't like water, which parts are hydrophilic that do like water. Some of these computational chemistry programs will analyze a genetic sequence or an amino acid sequence, and you can use that to do things like what's called molecular phylogeny, where you determine how closely related different species of animals are based on their genetic similarity or the similarity of amino acid sequences in a protein. And one that's really kind of cool, used a lot in the pharmaceutical business, is ligand docking. A ligand refers to a small molecule that binds to a bigger molecule. Usually we're talking about a small molecule that binds to a protein and initiates some kind of action, like a molecule binding to its receptor on the surface of a cell and then triggering some action to happen inside the cell. That's an example of ligand binding. But what these ligand docking programs allow you to do is you can bring in a 3D model of, say, of some surface protein that you're interested in, some surface receptor on the surface of a cell, and you can try to find other small molecules that will bind with the binding site on that receptor. It's a way of finding a small molecule that might bind to the protein and stimulate the protein, act as a substitute for the normal ligand that would normally bind to that, and to trigger the receptor. Or alternatively, you might be looking for a small molecule that binds to the receptor to inhibit the receptor. And so that's what a lot of pharmaceuticals do. I mean, a lot of drugs, they'll bind to a receptor to stimulate it. Like, if you don't have enough serotonin, you can get something that increases the amount of serotonin in the synapse, which is that would be a common form of antidepressant. Or alternatively, if you have a receptor that you want to inhibit, you could create a drug that they would inhibit a particular receptor and block some process or some reaction from happening. So you can do all of that in the computer. You can find small molecules that fit the binding site of a protein that you're interested in. Sheila is saying Molecular Maya doesn't run on the current 2023 version of Maya. That's wonderful. Yeah, I wonder if it works on an older version of Maya. I know the guy who writes Molecular Maya, so I'll get on his case and tell him to hurry up and make a new. I know the guy who writes EPMV too, and I think he's just kind of moved on with his life and decided not to keep updating it. Lots of chats. Oh, they said they're working on it. So if I can get my computer to work here, what's going on here? There we go. I just have some screenshots of some of these other programs that I was just mentioning. So these are screenshots of just a variety of some of the web-based viewers that allow you to view molecules right inside of a web page. These all happen to be based on Java. Like JMOL is a really popular one. This is one that's it's called NGL. It's based on WebGL, which is graphics library. It's basically a sort of like a graphics rendering tools that are built right into your operating system or right into your web browser. This, I believe, is the one that's currently available from the Protein Data Bank, so you can view a model right in the Protein Data Bank, and you can. It looks static here, but you can move that thing around. You can rotate it. You can change to different kinds of representation. Like right now, it's a ribbon model, but you could change it to a CPK model or a surface model or whatever you want. These are screenshots from 3 of the desktop viewing programs. So VMD in the upper left, that's one I'm not going to show you, but you will learn Chimera and Pymol. Here's a screenshot of what Molecular Maya looks like, if you can get it to run. So it's actually just this plugin that's this interface that pops up in Maya, and so you can actually import models directly into this. You can just enter the PDB ID number. The PDB is Protein Data Bank. So every protein that's saved in the Protein Data Bank has a 4-character ID number. And so you can just enter that ID number directly into Molecular Maya, and it'll go retrieve that model from the Protein Data Bank and bring it in and open it. Gail is the guy that wrote this. He's a researcher in molecular biology at Harvard, but he also runs a company on the side called Digizyme, which does a lot of molecular graphics stuff. And this is EPMB, the Embedded Python Molecular Viewer, written by Graham Johnson, who is a medical illustrator who I know from the AMI meetings. So I'll get on his case. I'll get on Gail's case too. I know both of them. But this, if you can get it to work, if they released updated versions of it, it would be a plugin that can run in pretty much any of the popular 3D programs. So it'll run in Cinema 4D, which is how I used to use it, Maya, 3ds Max, 3D Studio Max, or even Blender. And of course, Blender is the free 3D modeling program. So if you can get EPMB to work in Blender, then you'd be able to access all of it free. EPMB itself is free. Molecular Maya is free. You just have to find a 3D program that'll work inside of. Here's a screenshot of Marvin Sketch, the chemical drawing program that I'll introduce to you later in the course. So over on the left, you have all different kinds of bonds and things. You have the zigzaggy carbon, long carbon chains. You have bonds that'll come out of the screen towards us or go away from you. You even have some ring structures. So you've got, like cyclopentane, the 5-sided ring, cyclohexane. You've got benzene, the 6-sided ring with double bonds in it. So you can automatically draw these ring structures. You've got a bunch of common elements over here on the right. Of course, you've got your hydrogen, carbon, nitrogen, oxygen, sulfur, fluorine, phosphorus, chlorine, bromine, and iodine. So some of the common things that you would find in a lot of biological molecules. There's also a little miniature version of the periodic table here. You can click on that and actually get any atom you want. I mean, if you wanted an atom of platinum or an atom of rubidium or something like that, you could get it from in there. So you can draw these models. They initially, you draw them flat in 2D, but then the software will actually calculate the bond angles and draw it as a 3D model. And you can then export it for bringing it into your favorite 3D program. And last thing to mention to you, there are certain file formats that are used specifically for storing this kind of molecular data. So it's a file format specifically for molecular structures. The first of these to be produced was the file format called PDB. So if you see a file that's, hemoglobin.pdb, that means it is a PDB file of the hemoglobin molecule. And the PDB file ending is short for protein data bank. So it's a file format that was developed specifically for that protein data bank when it was created back in the 1970s. And that format is still around. The majority of models that I've been showing you in this class, the majority of the models that we're going to work with in this class are all PDB files. There's another format which is somewhat less common, but you still see them around, the MOL format. So it would be, hemoglobin.mol. This is the molecule format produced by MDL Data Labs, which was the company that created WebLab Viewer Lite, and then later produced that web-based molecular browser called QIIME. So they developed their own molecular model format back in the 90s, and so you do see things are available in this MOL format as well. But there's a whole bunch of them. Like every piece of molecular visualization software seems to have its own proprietary molecular model format. MMCIF is one you sometimes see. That's short for macromolecule crystallographic interchange format. And I forget what some of the others are short for. But as I say, a lot of these are proprietary formats from other molecular visualization programs. Fortunately, the molecular visualization tools that we're going to use in here, which would be Chimera and PyMol, they can usually open just about anything. If it's a 3D molecular model file format, they'll probably be able to open it, especially PyMol. I mean, I don't like PyMol as much as Chimera, but one advantage to PyMol is that it'll open almost anything you throw at it. Whereas Chimera is a little bit more limited in what kind of files it'll open. So that's that. That's probably maybe more information than you really wanted about this stuff, but I've always thought it's important to have kind of a historical background and also to understand a little bit about X-ray diffraction technology, especially to have an understanding of what they mean when you see, resolution of 2.2 angstroms or something, knowing is that a good quality high resolution file? Is that a low res file? Just being able to understand some of the information that you're going to start to see as you look into these molecular models in the protein data bank. Speaking of which, let me just open that up briefly. I'll come back and show it to you in more detail later. But if I go in here, it's the name of the website is not like proteindatabank.org. It's actually rcsb.org. RCSB is the acronym of the lab that actually hosts it and runs it. It's the Research Collaboratory for Structural Biology. That's where the RCSB comes from. But if you open up rcsb.org, you get the protein data bank. And like I say, I'll come back to this later. There's some amazing tools in here. Like there's this thing called PDB 101 that lets you explore, all kinds of molecules that are related to different aspects of human physiology. This is all about diabetes. These are the molecules involved, like, or at least the proteins, I should say. There's the glucagon receptor. Here's the insulin receptor. There's insulin itself. So you can access these different things from this PDB. Here's another entry all about energy production in a cell. So there's ATP synthase, which is the very complex molecular motor that's responsible for making ATP. And then you got all your other molecules in here involved in energy production and energy transfer. But we'll come back and talk about that again later. But the main thing you do with the protein data bank is, you can just enter something like molecule, like hemoglobin, just enter the name, and it'll search for them. And it actually found 3,529 different structures with the name hemoglobin in them. The trick with the protein data bank is being able to scroll through here and know which one is just plain old vanilla hemoglobin, because a lot of these are going to be, hemoglobin bound to something else. A lot of them are going to be like, I don't even know what the heck this thing is, lumbricus erythrochlorinate. Well, yeah, whatever that is. I mean, I can tell a lot of these are just hemoglobin, but structure of greyhound hemoglobin, like dogs, yeah. Crystal structure of dog hemoglobin, there's another one. I mean, dog hemoglobin is probably not that different from human hemoglobin. I bet if you created a model of them and put them side by side, nobody could tell the dog hemoglobin from the human hemoglobin. But if you really wanted human hemoglobin, you can narrow these down by species. So if we just limit ourselves to Homo sapiens, we still get 788 of them. Or we could, go back. Let's see, this is hemoglobin, right? Yeah. So, where are you? Oh, there it is. We could search for Equus cabeus, which is the Latin name for the horse. So if we really wanted to find Max Perritz's model of horse hemoglobin from 1960, I guarantee it's in here somewhere. So there are only 61 of them. So let's see if Perritz's name pops up in here someplace. You can also narrow it down by date, in which case we could definitely narrow it down to his horse hemoglobin. Let's do that. Let's narrow it down. So Equus cabeus, X-ray diffraction. Notice here you can refine the models by their resolution in angstroms. Let's say early release date. It says there's only one. 3-dimensional Fourier synthesis of horse deoxyhemoglobin at 2.8 angstroms resolution by Max Perritz. I mean, he actually published this structure in 1960, but it wasn't until 1970 that he actually had a digital version of this to publish. So then you can click on these and you can view them in one of those viewers that I was talking about before. This looks like NGL viewer. Oh, nope. WebGL. There's NGL. So you can rotate this around in 3D space. You can change the style. This is a cartoon, which is also a ribbon model. We could do a surface model. So there you see the 3-dimensional surface of the protein. We do a space fill. So, that's our space filling or CPK model, or licorice. And that's like a line model. But now you can see the heme groups in the hemoglobin. Those little rings, there's 4 of them. Those are the heme groups that actually hold the oxygen in the molecule. So anyway, we'll come back and explore this in more detail in the future. But just thought I'd quickly point out to you, the protein data bank and roughly how it works. But if you get into any of this kind of molecular illustration work, and there's a lot of it out there, with pharmaceutical companies, but also just because so many of the breakthroughs in medicine are things that are happening at the cellular and molecular levels. There's an awful lot of work involving this kind of stuff. So you'll want to get to know the protein data bank and know your way around it and how to use it. So, all right, that will do it for today. Let you go a couple minutes early for a change.